Good day, this is Dr. Fredericks again, and I'm bringing to you another video, this time focusing on correlations. This video is intended to be a brief review, essentially, because previously we have covered correlations, but I want to use this to reintroduce correlations as a precursor to regression analyses. Correlations are a statistical method used to measure and describe the relationship between two variables, and a relationship exists when changes in one variable tend to be accompanied by consistent and predictable changes in the other variable. A correlation typically measures two aspects of the relationship between variables, the first being the direction. And in a positive relationship, the two variables tend to change in the same direction, and this is indicated by a positive correlation coefficient. In a negative relationship, the two variables tend to go in opposite directions. This inverse relationship is indicated by a negative correlation coefficient. And so here I have two scatter plots. In A, on our left, we have the relationship between income and weight for men, and on our right, we have the relationship between income and weight for women. And if we look at the first scatter plot to our right, what we can see is there's a positive relationship between income and weight for men. And so as income increases, so does weight also increase for men. However, for women, as income increases, weight decreases for women. And so for men, there's a positive relationship between income and weight. For women, there is a negative relationship between income and weight. Now, important to note is that this dotted blue line, we can call this the line of best fit, let's say, right? Essentially, if the points fell on that line, we would have a perfect positive or perfect negative correlation, and we'll talk about that later. Essentially, the closer your points are to this best fit line, the stronger the linear relationship between the two variables. Now we can stop and think about reasons as to why this relationship exists. Maybe for men, as they make more money, they want to eat out more, go to nice restaurants, and this is just hypothetical. I'm not a researcher that investigates these variables. And then when we look at the relationship of income and weight for women, one could say, well, maybe as women increase in regards to their income, they have to work twice as hard as men do. And so they don't have as much time, for eating and pleasure. And I don't know, again, these are just hypothetical assumptions that I'm making. The truth of the matter is, correlation does not imply causation, right? And so the relationship between two variables existing does not explain why the two variables are related or how they're related. So we can't make any causal claims as to why this relationship may exist for men versus women. The only way we can make a causal inference about two variables that are related is if we had an experiment or an experimental design implemented where we manipulated one of our variables that we think are going to be the causal variable. If we manipulate our variable, conduct an experiment, then one can say X causes Y. Otherwise, we can say is that there is a relationship between these two variables. Without an experiment, there is no way to be able to infer causation. And so the second aspect of two variables that the correlation measures is the strength of the relationship between those two variables, which essentially focuses on the consistency of the relationship. And with the scatter plot on my left, you see a pretty strong positive correlation between two variables. One is indicated by the high correlation coefficient, 0.83. But the next thing that we can note or observe is that the points on the scatter plot are almost resembling a straight line or pretty close to a imaginary straight line, if you will. And again, that indicates to us the strength of a relationship. On my right, what you have here is a negative perfect correlation. So I want to talk more about perfect correlations. And so there are three ways that you may have a perfect correlation. The first way is that it occurs when everyone has the same exact score on two different variables, right? So let's say we want to look at the relationship between GPA at the beginning of a semester and GPA at the end of a semester. Of course, we know if we're looking at the same semester, your GPA isn't going to shift. And so for everyone in that sample, one can assume that the GPAs at the beginning and at the end, that's before the GPA is recalculated, they're going to be exactly the same. And so if everybody has the same score for beginning semester GPA and end of semester GPA, then that is one instance in where we can have a positive, perfect correlation. The next instance is when everyone's score on one variable differs by a constant from their score on the other variable. So let's say if we looked at GPA from one semester to the next, and for everyone's GPA in the first semester, it was, let's say, 10 points lower than their GPA of the second semester. For everyone, you have this constant increase of 10 points or 0.1 point, right? That is another instant in which you may have a perfect correlation. And I just want to interject, these examples are not necessarily realistic, but I just want to have you get an idea of what a perfect correlation could look like. And third, it could occur if everyone occupies the same position in a normal distribution for one variable that they occupy for the other variable. And one great example of this is looking at z-scores, for instance, right? So z-scores gives you the relative location of a particular raw score in a distribution. So let's say we're looking at the relationship between GPA and study time. And so let's say for each individual, of course, we're going to have a score for study time and a score for GPA. So let's say for the person with the highest GPA, they also had the highest study time. For the person who had the second highest GPA, they also had the second highest study time. And so forth until you get to the person with the lowest GPA, they also had the lowest study time, right? And so if the positions are exactly the same, and of course, when we talk about GPA, that's measured on one scale. Study time could be measured in minutes, in hours, right? And so they're measured on two different scales. But when we talk about the position that they occupy, first, second, kind of like ranks, right? First, second, third, and then being exact in terms of their positions in relation to the distribution of scores, then we are possibly looking at perfect correlations there. And so the Pearson's correlation is one of many correlation coefficients, and Pearson's are, as it's also called, focuses on linear relationships between two variables, and so it's a measure of direction and strength. And Pearson's R ranges from -1 to +1, where +1 denotes a perfect positive correlation, -1 denotes a perfect negative correlation, and 0 denotes a total lack of a correlation or a relationship between two variables. When we're using and interpreting Pearson's R, there are a number of situations in which we could use this correlation coefficient. And there's 4 instances. 1, prediction. And so if two variables are known to be related in some systematic way, it is possible to use one of the variables to make accurate predictions about the other. And that's essentially the base of our regression analyses, which we are going to look at next. Also, validity. And so one common technique for demonstrating validity is to use a correlation. And so, for example, if a new test actually measures intelligence, then the scores on the new test should be related to other measures of intelligence, right? If this indeed measures what we think it's going to measure, then they should be related. To evaluating the validity of a measurement procedure, we can also use correlations to determine reliability. And so a measurement procedure is considered reliable to the extent that it produces stable, consistent measurements. And so for instance, let's say I wanted to measure type A personality trait. I may take a group of individuals and measure them using the type A scale at time 1, and then maybe a month later I'll measure them again using the same type A scale at time 2. If the type A scale is indeed reliable, one would expect that the relationship between the first and second administration of the same scale would be extremely high and positive. And lastly, theory verification. And so many psychological theories make specific predictions about the relationship between two variables. And so such predictions can be tested by determining the correlation between two variables, right? And so past literature and theories, if they support a notion of a relationship existing, one can simply test that relationship to verify a theory that has been put in place or has been created or derived. And so there are two potential formulas that we can utilize for Pearson's R. Now there are variations of each of these formulas, mind you, but on your left there's the formula for Pearson's R for your raw scores, and on your right the formula for your z-scores, right? And so if you're looking at raw scores, essentially the top of this ratio or the numerator, it kind of looks like your sums of squares, right? However, what it is actually called is the sums of products or the sum of products, right? And so you're looking at the products of the two variables and how they vary together. And so your z-score equation is essentially focusing on standardized score. So it's also known as your standardized score equation, right? And so in order to utilize this equation, you would have to have taken your raw scores from both variables, x and y, standardize each of these raw scores, right? And so you would need your mean and your standard deviation to essentially transform each raw score into a z-score, and then you can utilize this equation to calculate your Pearson's R in the event that you were looking at z-scores. Thank you so very much, and I will see you again, or rather talk to you soon.